Good morning, AP Physics 2 students. You should be watching this on August 26, 2019. This is Mr. Williams. I'm sorry that I can't be with you today, but I am going to do my best to try to get you started on Chapter 11 in your book. So, Chapter 11 starts on page 318. I will be pointing out some things in the book as we go along. But first, I'm going to review energy concepts from last year. It has been a while since we looked at them, and we're going to be building on them for about a month or so going forward here. First thing I want to remind you is last year we learned about a couple different types of energy. We learned about kinetic energy, Kinetic energy is the energy of motion, and the symbol for kinetic energy is capital K. Kinetic energy is equal to 1/2 mv squared if you're going in a straight line. But of course, as we learned last year, objects can also they can rotate, they can go in circles. And so the kinetic energy associated with rotation is 1/2 times the moment of inertia, which is the rotational mass, multiplied by the angular velocity squared. So the total kinetic energy of a system, if an object was going forward and turning at the same time, so like a wheel on your bicycle, the wheel is turning and the bicycle is moving. So the wheel is going forward and it's turning. So it's got both translational or straight line motion, and it has rotational motion as well. Then the total kinetic energy that your bicycle wheel would have would be your translational or straight line piece, which is 1/2 mv squared, plus your rotational piece, which is 1/2 moment of inertia times angular velocity squared. We also learned about potential energy. We learned about two big types, though there are others we have not spoken about yet, and we will learn about them this year. The generic symbol for potential in physics is capital U, although last year I tended to use PE, capital P, capital E for potential energy. But this year we're going to use more grown-up terms. So the gravitational potential energy is going to be, there are a couple types, but gravitational potential would be mgh, the mass of an object times the acceleration due to the planet that it is near, multiplied by the change in height above that planet's surface. That would give you the change in the potential energy of the object near that planet's surface due to gravity. And another type of potential energy we talked about was the spring potential energy. So if you compressed a spring and then an object like boinged away from it, so you have an object here, you've pushed the spring, and then you let it go, then the potential energy that's stored in the spring over here is going to be 1/2 times K, which is the spring constant. It's a measure of how springy the spring is. 1/2 times K times x squared, where x is the distance that you compress the spring before you let the object fly off. So that should bring back some good memories. Here's another term that I want you to remember: mechanical energy. So mechanical energy is the sum of all potential energies and all kinetic energies. So if you added up all the potential energies you have and all the kinetic energies you have, that would be however much mechanical energy you have. And mechanical energy is conserved. So you should remember from last year that conserved has a special meaning in physics. Conserved means however much you have at the end, you had that same amount at the beginning. That the total amount doesn't change. If you add up however much you have at the start, that's exactly how much you're going to have at the end. So mechanical energy is conserved. And we can state this mathematically a couple ways. This is the way I tended to state it last year. And I would like take the initial kinetic plus, and sometimes you'd have more than one type of potential. Like if I might have some potential initially for gravity and some potential initially for the spring, but whatever they are, you add up all the potentials initially, and that has to be equal to all the kinetics finally plus all the potentials finally. And this was a statement of conservation of energy for us, but it was really a statement of mechanical energy being conserved. This is true as far as it goes. However, there are other types of energy in the universe. When you look at all the types of energy that there might be, it's not just kinetic and potential. There's other types of things going on in the universe. You have thermal energy. So thermal energy is associated with heat. You know this, like if you ever ran around our school's football track, you got hot. Like your body started getting hot. You could feel it coming off of you. That's the thermal energy that you were experiencing it right then. And then, of course, there's light energy. The sun sends light down to our planet and plays a role. I mean, that's the foundation of all life. Then there's sound energy. You throw a ball, it hits a wall. Well, some of the energy goes into the wall, bouncing back off, into the ball, bouncing off the wall. Yeah. So some of your energy is still in the ball. Some of the energy goes into heating up the ball, and some of it goes into heating up the wall, and some of it goes into heating up the air. That's true. But then, of course, some of the energy goes into sound. So that sound gets transmitted all the way around, and other people who are far away can hear the ball hitting the wall. Another type of energy that can be created is electrical energy. And at the end of last year, we talked about it just a little, how we can make electrical energy by you can push a magnet in and out of a coil of wire, and you can make electrical energy that way. There's other kinds of energy that I'm not going to talk about now, but the point I want to make is there are all kinds of energy that are not mechanical energy. We're going to be exploring all those other types of energies in much greater depth going forward here. The really tricky thing I want to lay out for you is that thermal energy cannot be easily transformed. So you know how some kinds of energies can be real easily transformed. So you can transform the potential energy of a ball real easy. You pick it up, and then when you got it above your head, it has a whole heck of a lot more potential energy than it had when it was down on the ground. So you're easily able to basically store energy inside the potential between the center of the earth and the center of the ball. There's no easy way to store energy thermally, which means that once energy becomes thermal energy, it's almost impossible for humans to get useful work back out of thermal energy. There's some cases where we can do it. I'm going to go over one just here in a minute, but it's not very effective. It's not very efficient. It's not very useful. I mean, it can be useful, but it's highly inefficient. So for most practical purposes, thermal energy is lost, quote unquote, lost to human use. When you hear people say that energy was lost, well, of course, that's not true, because you know from conservation of energy that energy is neither created nor destroyed. But what people often mean by that is that the energy is lost to humans, that we can't use it anymore because it just became heat, or people say heat. What they mean by that is usually thermal energy. We're going to be exploring a lot this year some of the details of that. Here's another little piece of review I want to do with you. I'm going to get this sheet of paper out of the way. Last year we learned the WorkEnergy Theorem. And the WorkEnergy Theorem essentially says that a system's total energy changes by the amount of work done on a system. This year we're going to be paying a great deal of attention to the words on and by. But we're not going to get into that too much right now. I'm just going to give you a heads up that that's coming down the pike. If we were to state this mathematically, we would say the change in energy in a system is going to be equal to, well, what are all the different types you could have? I mean, you could have kinetic energy changing. You could have some changes probably in your potential, both spring and gravitational. You could have some changes in your thermal energy. Something could get hotter or colder. You could have changes in your chemical energy, like if you're pushing something, like you're pushing your little cousin on a wagon or something. You could have a change in the stored chemical energy inside your body. I can't even think of all the different. You could have changes in the sound energy and light energy. I'm not even getting into it, all of it. I'm just going to put dots. There could be tons of changes in all the different types of energy. So the total energy change is the sum of all the little energy changes that happen. And when you add all those little energy changes up, all those little energy changes have to be equal to the work done on the system. So however much work got done on this system, the change in the energy, when you add it all up, has got to be equal to the work done. So let's just review here what work is, because I haven't really stated that for you now. You may or may not remember. I said that work was an energy transfer, I believe. Let's see here. I'm trying to look and see if I said that already, and I can't see it. So I'm just going to say it now. Work is an energy transfer. That's really what it is. And we defined it last year as work is equal to the force parallel times the displacement. Now, this is a vector and this is a vector. So let me remind you of an example I showed you last year in class. If I take the trash can in our classroom and I push on it, and I push exactly in the same direction, my hand's not angled up or down, I push exactly in the direction the trash can is moving, then the force vector is lined up with the trash can's displacement vector. So I'm pushing the trash can, and the displacement vector for the trash can is lined up with the force vector from what I'm putting on it. Then it's just force times distance equals the work. Now, of course, this is an AP class. It's not a regular class. So that means we talked about what happens if there's an angle between the force you apply. Like, if, say I'm pushing on this trash can, but I'm pushing down at an angle, or I'm pushing up at an angle, or I'm pushing sideways at an angle. So the trash can starts to move this way. Its displacement is like this, but my force angle is like this. So then I have my force going this way and my displacement going that way. If there's an angle between the force and the displacement, you should remember from last year that the work is then equal to the force times the displacement times the cosine of theta, where theta is the angle between the force and the displacement. Now, whenever interactions like this occur, heat is always created. Or, sorry, I shouldn't say heat. I should say thermal energy. Thermal energy is always created. And thermal energy is, for practical purposes, basically lost for human use. So we're going to now learn something new. Here's something new for us. We're going to talk about efficiency. Efficiency, the symbol for it is like a little lowercase e. I can't make it like it does in your book. If you look in your book on page 320, equation 11.12, page 320, equation 11.2. Starting to get dark in here. So 11.2. Then you will see that symbol. It's just basically a little e, but I'm not making it that way. I guess I could try. Come on. Let's see. It looks like that. It's just a regular old like e. And that's a symbol for efficiency. So let me see if I can make it. So efficiency is equal to, it's what you get in terms of energy divided by what you paid. So let me give you an example. What you paid is how much energy you spent. How much energy you spent. And what you get is basically how much energy got produced. So a pretty good example would be if you walked up a flight of stairs. So let's say that you walked up a flight of stairs. You would gain gravitational potential energy. But how much energy actually came out of your body when you went up the flight of stairs? Well, it was more than the gravitational potential you get at the end, because as you climbed up the stairs, some energy went out of your body because you got hot. And some energy went out of your body to make the clomping sound as you clomped up the stairs. So you're losing energy in addition to the gravitational potential. I don't know. Let me make up some numbers. Let's say that you climbed up the stairs, and when you got up to the top, your mass times the height was, I don't know. Let's do an example. Let's say that you have a mass of 70 kilograms, and you climb up some stairs. They look like this. And the stairs have a height of, I don't know, 10 meters. So the potential energy that you would get is 9.8 times 70 times 10. So I'll get it exact for you. 9.8 times 70 times 10. You got 60 joules. 60 joules. That is what you get. So your efficiency would be about this. So if your efficiency was, let's see, if what you get is 60 joules, what did you pay? How much energy came out of your body? Well, it was more than that, I can guarantee you. Let's say it was about 24,000 joules. Because that would be about right. So 24,000 divided by that. I did it backwards. 6860 divided by 24,000. There we go. That's a 28.6%. And since I made these numbers up, I made them too nice. The general efficiency of the human body is about 25%. But you think about it, if you think about that, that's nuts, man. We are highly inefficient creatures. Just walking around, you're losing heat energy all the time. It's spilling out of your body. 75% of your energy is getting lost to thermal energy. Oh, dude, that's nuts. Humans, our bodies are not energy efficient at all. So what causes this inefficiency? A lot of people over the years have gotten trapped by this question. A lot of people think, oh, if you could just design a perfect system, like a perfect human or a perfect machine or a perfect something, you could get 100% efficiency. Unfortunately, I'm here to tell you that it actually can't happen. You need to know straight up front that it's completely impossible to get 100% efficient anything. Creature, machine, nothing is going to be 100% energy efficient. In fact, 50% efficiency is really good, really good. Almost nothing is 50% efficient. If you make a machine that's 50% efficient, dang, like that's amazing. So in your book, they talk about an example on page 321 of a power plant that burns fossil fuels to make electricity. And the example they give you, it's about 35% efficient. So fossil fuel plants, like a coal plant. So a coal plant, COAL, plants are about 35% efficient. So that's more efficient than the human body, but that's not saying a lot because we're pretty inefficient just all by ourselves. There are two reasons why a creature or a machine might be inefficient. It could be because of processes, and you could improve those processes by designing better processes and lose less energy. That usually is a very small amount. We're talking about 5-10% is due to processes. Then there are things called fundamental limitations on page 320. There are certain physical laws we're going to learn about in this chapter and the next that just mean you can't get above a certain efficiency depending on your design. And fundamental limitations are things that neither you nor I nor anybody else can get around. So I want to point something out to you on page 321. So on 321, there's an energy efficiency problem strategy guide, and I'm going to let you look at this at home. So I'm pointing it out to you right here. When you get home, I want you to look at it. Also, I want you to look at this example down here at the bottom of page 321. It compares the light bulb efficiency of compact fluorescence and incandescence. When I was a kid, we used incandescent light bulbs, 75 watts, and a compact fluorescent that produces the same amount of light energy is about 15 watts. So each of them is going to produce 3 watts of visible light energy, but the incandescent draws 75 watts of electrical energy, whereas the compact fluorescent only draws 15. That means that a compact fluorescent light bulb is 20% efficient, and an incandescent light bulb is only 4% efficient. 4%. That means 96% of the energy produced at the electrical power plant is lost to thermal energy in a traditional incandescent light bulb. So 96% of the energy that the power plant made is going to be used in your house by your incandescent light bulbs to heat up the room. That's a lot of heat. Like, those light bulbs make a lot of heat. I want you to think about that. That's pretty nuts. That's really all I wanted to talk to you about today, is some of the fundamental limitations on efficiency. I also want to emphasize to you that when things get turned into thermal energy, that process is essentially irreversible for the purposes of human use. And I'm going to end this now. I want you to take the remaining 20 minutes or so of class, or 15 minutes, however long you have, and I want you to do problems 1 through 4. On page 345. So these are problems number 1 through 4 on page 345. I want you to do those now, and if you don't get them done, they're due for homework. And we are going to, these will be due on Wednesday. I'll go over the next section or two tomorrow. Thank you for your attention, and good luck with the work.